carrying this logic further, we can ask a more interesting question. What if I remove the entire PMOS stack? What if I just remove that entire PMOS stack? What will happen? Clearly now no input is going to be connected to my PMOS transistors, and therefore the capacitance is dropped not by half but more than half. So this brings us to the idea of ratioed circuits. So a static CMOS implementation is like this: pull up network, pull down network. The idea in a ratioed circuit, or is also called a pseudo NMOS logic. Okay. Is like this. Pull down network. The advantage in the static CMOS logic was that there was no path for current to flow from supply to ground in the steady state. Of course, what we are doing here now is we are connecting that a PMOS transistor to ground with a gate connected to ground always. So when the pull down network is active, obviously there is going to be current that will flow from supply to ground in steady state. So this is not a good thing. We will see how to avoid this problem. But first let us see what advantage we get in terms of the logical effort. Okay. What we have been able to do is completely eliminate that PMOS pull-up network, right? And that is what is your killer for the logical effort always. Okay. So the other obvious problem in this is that when my pull down network is conducting and my output is low, will the output go all the way to 0? No, it can't go all the way to 0, right? Because I have a fighting between the PMOS transistor and the NMOS stack. So therefore, the output Y, VOL, is going to be greater than 0 in this pseudo NMOS logic. We will first calculate what that is. Okay, so let's consider a pseudo NMOS inverter. This is a pseudo NMOS inverter. Only one NMOS transistor is connected to the input A. A is not connected to the PMOS transistor. Okay. So I now want to calculate what happens when A equal to VDD. Y will be VOL. Of course, VOL now has to be close to ground, right? Otherwise, this gate is going to be useless. So in what region of operation will my NMOS transistor be? In what region of operation will the PMOS transistor be? Let us not jump there. Let's write it down. NMOS, PMOS, right? VGS, VDS. What is VGS for the NMOS transistor? VDD. VDS. Yeah? VOL. Now, VDS compared to VGS minus VT. Where is it? Therefore, region is linear because VOL is much smaller than VDD minus VT. What about the PMOS transistor? What is VGS? Minus VDD. VDS. VOL minus. Now, which region is the PMOS transistor? You have to do VGS minus VT. Right? That's a reasonably large number, about 0.3 volt. If VDD is 1 volt, this is about 0.3 volt, so that will be about 0.7 volt. VOL minus VDD, where will it be? Very close to VDD. Therefore, this has to be saturation or velocity saturation, depending on whether it is short channel or long channel device. Right? So, let's say it is in velocity saturation. Okay. So, now we go through the same drill. Equate the current in both of them and then we can find out what VOL will be. Okay. So, what is VOL? IDSN is in linear region. Therefore, this is I can say Kn prime Wn by L into VDS, that is VOL, into VDD minus VT n minus VOL by 2. Right? Now, what is IDSP? Kp prime Wp by L into Vd sat P into what is this? Minus VDD, right? Minus VTP minus Vd sat P by 2. Clear? Now, VOL is a very small number. So, therefore, this VDD minus VTN minus VOL by 2, I can approximate, right, as VDD minus VTN. So, therefore, I will now say IDSP equals minus IDSN implies Kp prime Wp by L into Vd sat P into VDD plus VTP plus Vd sat P by 2. Right, I want to bring the minus sign out, equals minus Kn prime Wn by L into VOL into VDD minus VTN. Clear? Therefore, I can now cancel out these two things and I will get VOL as Kp prime into Wp into Vd sat P to VDD plus VTP plus Vd sat P by 2 by Kn prime into Wn into VDD minus VTN. Okay. So what does this tell you first of all? In order to achieve a certain VOL so that the circuit can even function logically correctly, I need to have a certain WP by WN ratio. If the PMOS transistor is extremely strong, then when the pull down network is active, the PMOS transistor will try to pull the output closer to VDD and will not allow the pull down network to go to 0. And therefore, in that fight, output will go and land in between 0 and VDD, and that is completely determined by what your WP by WN ratio is. That's why this is called a ratioed circuit. Because it does not even function if the ratio of these PMOS and NMOS transistors is not correct. Earlier I had mentioned that static CMOS is independent of gate size as far as logical functionality is concerned. It will work whatever size you put, whether you put 1/2, 1/4 or 10/1, it doesn't matter, it will function correctly. NMOS and PMOS. It's only for delay purposes that we actually made it 1 and 2 and all that stuff. Logically it will still function, but this circuit will not function unless you size it appropriately so that your VOL is met. So the way you do it is, you want a VOL, I'll give you a VOL and say, okay, size the inverter so that it meets this VOL first. Then you use this equation, calculate what my WP by WN should be. Clear? So which implies, now let's make some simplifications. Suppose this VDD plus VTP plus VD sat by 2, right? Suppose the VT and VD sats were such that these two terms cancelled out. Suppose, right? I'm not saying that VTP equal to minus VTN. I'm saying the VTNs and VD sat P together cancel out this term, right? Then it implies VOL is simply Kp prime WP by Kn prime Wn into VD sat P. This is the first order thing, but of course you don't have to make this approximation. I'm just trying to bring out this thing here. Okay. So what does this say? It says that WP by WN equals VOL into Kn prime by Kp prime into VD sat P. So if your VOL goes up, then WP has to go up. Correct? That's what this equation says. WP by WN is proportional to VOL. So if VOL has to come down, then WP by WN has to come down.